Welcome to this presentation on the longest subarray with sum k problem. In this session, we will explore the problem, the approach to solving it, and walk through its implementation. Let's dive in. The problem is simple. Given an array of integers and a value of k, we need to find the length of the longest subarray whose sum is exactly equal to k. For example, given the array with elements 10, 5, 2, 7, 1 and 9 and the value of k 15, the solution is a subarray of length 4. If no such subarray exists, we return 0. To solve this problem efficiently, we use a combination of prefix sum and a hash map. The prefix sum helps us track the cumulative sum of the array elements. The hash map will store the first occurrence of each prefix sum, allowing us to quickly check if we have encountered a sum that leads to a valid subarray. Key observations make the approach even more efficient. If the prefix sum equals k at any point, it means the subarray starts from the beginning of the array. If the difference between the current prefix sum and k exists in the hash map, we can calculate the length of the subarray between these indices. This gives us the longest subarray with sum k. Now let's break down the algorithm. We initialize the prefix sum as 0, the maximum length of the subarray as 0, and an empty hash map. As we traverse the array, we keep adding elements to the prefix sum. If we encounter a prefix sum that satisfies the condition we discussed, we update the length of the subarray. The algorithm works as follows. If the prefix sum equals k, we update the max length to the current index plus 1. If the difference between the current prefix sum and k exists in the hash map, we calculate the length of the subarray and update the max length. Finally, we store the prefix sum in the map if it's not already there. Let's now look at the implementation. In the first part of the code, we initialize the necessary variables, including the hash map and prefix sum. We also define a function that will take the array and k as inputs and return the length of the longest subarray. In the next part of the code, we iterate through the array, updating the prefix sum. If the prefix sum equals k, we update the max length. If we find a matching prefix sum in the hash map, we update the max length by calculating the length of the subarray from the earlier index to the current index. Finally, if we encounter a new prefix sum, we store its index in the hash map, so we can refer to it later if needed. This way we ensure that we are efficiently calculating the longest subarray. Let's walk through an example to understand how the algorithm works. Given the array with elements 10, 5, 2, 7, 1 and 9 and the value of k as 15, we start by initializing the prefix sum and max length. As we traverse the array, we update the prefix sum and check for conditions. Continuing with the example, at index 3 we find that the difference between the prefix sum and k exists in the hash map, allowing us to calculate the length of the subarray. By the time we finish traversing the array, the longest subarray with sum k is of length 4. Now let's analyze the time and space complexity of the algorithm. The time complexity is big of n, where n is the size of the array since we only traverse the array once. The space complexity is big of n because we store prefix sums in the hash map. The algorithm is efficient with linear time complexity and works with both positive and negative integers. It can be used in solving other subarray related problems, financial data analysis, and can be adapted for various use cases that require finding subarrays with specific conditions. In summary, the longest subarray with some k problem can be efficiently solved using the prefix sum technique combined with a hash map. The time complexity is big of n and space complexity is big of n. This approach is not only fast but also versatile in handling a wide range of problems. That concludes the presentation. If you have any questions or need further clarifications, feel free to ask, and thank you very much for your attention. Hello everyone, and welcome to this presentation on the problem minimize sort. In this session, we will explore an efficient algorithm and its implementation in C++. In this session, I will be guiding you through this exciting problem. The objective of the problem is simple yet intriguing. Given two integers num1 and num2, we aim to find an integer result that satisfies two conditions. The number of 1 bits in result must equal to the number of 1 bits in num2. The XOR between result and num1 must be minimized. The problem has straightforward constraints. We are given two integers as input num1 and num2, and we need to output an integer result that meets the specified conditions. To solve this problem, we use a couple of fundamental techniques. First, bit manipulation allows us to efficiently work with binary representations. Second, the counting of set bits, which refers to the number of 1 bits in a binary number. In C++, we can utilize the built-in function built-in pop count for this. We also apply a greedy algorithm to minimize the XOR. This involves prioritizing the most significant bits of num1 to reduce the XOR difference. If necessary, setting additional bits in the least significant positions. Let's break the approach into simple steps. In step 1, we count the number of 1 bits in num2 using built-in pop count. This gives us the target bit count for our result. In step 2, we iterate through the bits of num1, starting from the most significant bit and set bits in the result as long as the target bit is not met. In step 3, we still need more bits to match the count. We set bits in the least significant positions of the result. This ensures that the XOR is minimized while satisfying the required number of 1 bits. Here is the first part of the C++ code. We begin by defining a function minimize XOR. First, we calculate the number of 1 bits in num2. Next, we initialize a variable result to store our final result. Then we iterate through the bits of num1 from the most significant to the least significant, setting bits in the result until the target bit count is met. In the second part, if the bit count is still less than required, we iterate through the least significant bits and set them in the result. Finally, we return the result which satisfies both conditions of the problem. Let's walk through an example. Suppose num1 is 3, which in binary is 1 1, and num2 is 5, which in binary is 101. The first step is to count the 1 bits in num2, which equals 2. Next, we copy the set bits from num1. Starting with 1 1, we use 1 bit, leaving 1 bit remaining. Finally, we add an extra bit in the least significant position, resulting in 110. So the output is 6, which is 110 in binary. Now let's analyze the efficiency of our solution. The time complexity is big O of 1 as we only iterate through 32 bits twice. The space complexity is also big O of 1 as we don't use additional data structures. This makes the solution optimal for all valid inputs. To summarize, bit manipulation is a powerful tool for problems involving binary operations. Built-in functions like built-in pop count simplify implementation. A greedy approach helps in effectively minimizing the XOR value. That concludes the technical discussion. Do you have any questions or feedback? And thank you for your attention. Before we wrap up, don't forget to subscribe to my channel. Here I share coding tutorials, problem solving strategies, and much more. If you found this presentation helpful, please like, share, and subscribe. Thank you for your support, and I will see you in the next